Hello everybody, welcome into another lesson. So today we are starting the transformations unit. This is a 5-lesson series about transformations in the coordinate plane of points and even shapes. So there's a lot of ground to cover today. This is just a general introduction, but the following lessons we're going to talk about reflections of shapes and points. Then we'll talk about shifting of points. Then we'll even talk about rotation. And then we'll talk about dilation and shrinking. So today's just the general introduction. So here you have a point A at 3, 1 in the coordinate plane. If that's the original point you started with at 3, 1, that's called the preimage. You could think of it pre. That's, before there were any changes, because pre means before. So that's your starting point. And then this A with that mark to the side of it, with that apostrophe, is called A prime. That's what you would call it, A prime. At the point 6, 4, it's the image. The image occurs after you've made the changes to the preimage, which makes it become the image. Now, this is all going to tie in with talking about functions and mappings. If we recall from algebra, a function is a correspondence between a set of numbers, right? So, of course, in order for an equation to be a function, each member, or set of numbers even, to be a function, each member of the domain has to have one and only one number in the range. And then mapping is similar in the fact that it's a correspondence between images. So A corresponds to A prime. This is a mapping. And actually we use function notation for mapping, so that's how similar they are. We will use function notation for them. So let's get into some other definitions here. Alright, so let's now talk about a 1, 2, 1 function. So if it wasn't enough that we had functions, we're going to talk about a 1-to-1 function. Well, what the heck is a 1-to-1 function? So again, in general, for a set of numbers or system to be a function, each member of the domain, your x variable, your independent variable, however you want to call it, can have one and only one y variable relation, or the range, one and only one member of the range, or one and one only dependent variable, however you want to refer to it. A 1-to-1 function is such that each member of the range has one and only one member of the domain. So it flips it. And this is going to come in handy in Algebra 2 when we get into inverse functions. You'll see this a lot. And there's 3 tests we can use to determine if a function's 1-to-1. We're not going to cover that in this course. We'll cover that in Algebra 2. But in short, a 1-to-1 function is one where each member of the range has one and only one member of the domain. That's what 1-to-1 means. So the first one is it's a function itself. The second one is that each member of the range has one and only one member of the domain. That's why it's called one-to-one. So that's a one-to-one function, and we're going to do some exercises real quick to determine if a function is one-to-one. So let me make a table of values here real quick, okay? Let's do that. Of course, you'll have your x and your y values. X usually denotes the domain. X is usually your domain or your independent variable. It's what you put in. Y is your range and your dependent variable. X is also called your input, Y is your output. Because you put in an X, you get a Y value, right? Well, let's put in some values here. Let's just arbitrarily put in some numbers, and we'll determine if the function is one-to-one. These are all functions. Okay, so let's say I got 1, 2. I have 2, 4, 3, 6, 4, 8, and 5, 10. So this is a function because each member of the domain, 1 through 5, has one and only one value in the range, right? Each x value has one and only one y value. Now the question is this a one-to-one function? Well, the range 2, it only pairs with 1 for the domain. 4 in the range only pairs with 2 for the domain. 6 in the domain, 6 in the range only pairs with 3 in the domain. 8 in the range only pairs with 4 in the domain. And then 10 in the range only pairs with 5 in the domain. So yes, this function is one-to-one. This is in fact a one-to-one function because each member of the range has one and only one domain value. Let's do a couple more here. Alright, so let's see. We have the point 1, 6, -1, -2, 0, 3, 2, 6, and 3, 4. So here's another function where we have the x value of 1 in the domain with a y value of 6 in the range, an x value of -1 with a y value of -2, an x value of 0 with a y value of 3, then we have an x value of 2 with an x value of 6, then we have an x value of 3 with a y value of 4. So let's look at this. Well, it's a function, right? Because each member of the domain, all these in the domain have one and only one member of the range, right? You only see one number of each in the domain, so therefore it's definitely a function. Now the question is asked, is this a one-to-one function? Well, if we look at the range, we see 6 occurs twice. You can pair 6 with 2 in the domain, or you can pair 6 with 1 in the domain. So, if that's the case, if you compare a member of the range with 2 members or more of the domain, then this is not a function. Not a function, not a one-to-one function. It is a function, it's not one-to-one though. So this function is not one-to-one because you have a member of the range paired with 2 members of the domain. Alright, let's do like 2 more of these. I would drop it. Leave it to me. Typical me dropping stuff. Okay. Let's see. We have 4 and 19. 5 and 13. 6 and 17. 3 and 18. 2 and 21. Okay. So here's another function where you have given values of your x values, your independent variable, your input, your domain, 4, 5, 6, 3, and 2. Those correspond with your range, your y values, your dependent variable, your output of 19, 13, 17, 18, and 21. Well, this is definitely a function because each member of the domain occurs only once. And it's paired with one member of the range, one and only one member of the range. But is this function one-to-one? Well, look at your range. We only see each member of the range occur one time. And they're all paired with different members of, they're all paired with one and only one member of the domain. So this is a one-to-one function. This function is in fact one-to-one. I think you kind of get the idea of one-to-one functions. Those are actually pretty easy to determine. There's 2 more tests we can use in Algebra 2. We'll get to those at that time. But now, I got another definition to throw at you. It's called a transformation. We're going to talk about a transformation. A transformation is a one-to-one mapping. So if we have it's a one-to-one mapping, meaning that each image has one and only one preimage. So you could think of the preimage as your domain and the image as your range, right? The values you'll get out of the mapping. If this image had more than one preimage, it would not be a one-to-one mapping. And that can happen if you're using quadratic functions to try to map stuff. That will actually make it a non-transformation because then it would not be a one-to-one mapping. So we're going to do some examples here. Well, first we also want to throw in another term. I'm going to get rid of these for a minute. I'm going to keep up the coordinate plane. I want to talk about something called an isometry. We want to talk about an isometry, what one of those is. An isometry is a transformation that maps congruent segments, angles, polygons, etc. Alright, so an isometry is a transformation that maps congruent segments to congruent segments, congruent angles to congruent angles, congruent polygons to congruent polygons, etc. And so basically what that means is the size doesn't change. There's no change in size. So a reflection, for example, is not a change in size. If I take this whiteboard and reflect it in a mirror, I certainly haven't changed the size. I'm just reflecting it. If I take this whiteboard and move it across the room, which is shifting it, I certainly haven't changed the size of my whiteboard. I have just simply shifted the whole thing. If I rotate this board and I turn it around, or if I turn it on its side, I rotate it, I still haven't changed the size of the board. I've rotated it. Those are all examples of isometries. Now, if I dilate this board, like if I make it a lot bigger, I add on to it, or I shrink, I take parts of it apart, then I've changed the size, which would make it not an isometry. But we'll cover all those in those respective lessons. But we're going to talk a little bit about here finding the image and the preimage. We're going to have a function here. Dang it, that's not what I wanted. There we go. Alright, so we're given a function here, just f of x equals 5x minus 7. Which would occur, you can essentially use this for mappings and transformations also. Find the image of 8 and the preimage of 13. So we are given a function here, 5x equals 5x minus 7. Find the image of 8 and the preimage of 13. Alright, well, let's come over here, we'll find the image. So, if we're asked to find the image of something, what that means is you're going to take the value of the image, which is 8, and stick it into your function. So the image, to find that, is going to be f of 8, right? Since that is your image, is 8, f of 8, you put that into your function, you'll get 5 times 8 minus 7, which would equal 40 minus 7, which would give you an image of 33. So the image of 8 would be 33. So that's just a matter of taking the value of your image, sticking it into your function. Now, to find the preimage on the other hand, the preimage is the value of the function itself, not the value you're going to stick in. To find the preimage, which would be before the transformation, you're going to take the function itself, the 5x minus 7, you're going to set that equal to the value of the preimage, which is 13, which then would give you 5x equals 20, which would give you an x value of 4. So the preimage would be at 4. When you have a preimage of 13, when you have a preimage of 13, the value of the image would be at 4. So there's the preimage of 13. If the image is 13, the preimage is 4. And then the image of 8 is 33. So to find the image, you stick the value of the image into the function. To find the preimage, you set the function itself equal to the value of the preimage. And then you solve for the variable. Alright, I have another one that's sort of similar. so let's see. Alright, so this time we are given that g of x equals 8 minus 3x. Find the image of 5. The 5 should be down here. My bad. I don't know why I wrote it up here. So find the image of 5 and the preimage of 10. So let's go ahead here and let's find the image. Again, to find the image, you'll take the value of your image, put it into your function. So this would be g of 5, since 5 is the value of the image. That would, of course, equal 8 minus 3 times 5, which would give you 8 minus 15, which would give you negative 7. So the value of the image of 5 would be negative 7. That's your image. Now, let's go on to finding the preimage. To find the preimage, you set the whole function itself, that 8 minus 3x, equal to the value of the preimage, which would be 10. Well, that would end up giving you 3x equals negative 2. So x would equal negative 2/3. So the preimage of 10 would be at negative 2/3. That would be the preimage. So yes, you'll get fractional answers sometimes. You'll just have that. Alright. Now, here's a little bit different. F of x equals x squared plus 1. Find f of 3 and f of negative 3. Is f of x 1 to 1? So they're actually trying to illustrate a point with this here about one-to-one functions. So we're given that the function f of x is equal to x squared plus 1. They're asking us to find f of 3 and f of negative 3. Then we have to determine, is this function one-to-one? So let's find the f of 3 and f of negative 3 first. So f of 3, of course, would give us, we put that in for where the x is, that would give us 3 squared plus 1, which would give us 9 plus 1, which would give us a value of 10. So f of 3 equals 10. Now let's find f of negative 3. Well, that's going to give you negative 3 to the second power plus 1, which would still give you 9 plus 1. Well, coincidentally, f of negative 3 also equals 10. So granted, this is a function. You have two separate members of the domain that have one value in the range. However, this value of the range, 10, has two values in the domain of both plus and minus 3. Therefore, this is not one-to-one, since that value of the range, 10, has two members of the domain of 3 and negative 3. So this is not a one-to-one function. All right. Now, let's see. Alright, so a sort of similar problem. We're given the function h of x equals 6x plus 1. Find h of 1/2 and h of negative 1/2. Is h of x 1 to 1? Well, let's go ahead, let's solve for these two values first. So let's stick in h of 1/2. That, of course, would give you 6 times 1/2 plus 1. Well, what is 6 times 1/2? That's 3. So you'd have 3 plus 1, which would give you a value of 4. So h of 1/2 is equal to 4. Now let's find h of negative 1/2. That would, of course, give you 6 times negative 1/2 plus 1. Well, what is 6 times negative 1/2? That's negative 3. So you'd have negative 3 plus 1, which would give you a value of negative 2. So we've solved for the values, but is h of x 1 to 1? Well, we have two members of the domain that have different values of the range. It's definitely a function, and you don't have the same repeating members of the range. So each of these members of the range, 4 and negative 2, have one and only one member of the domain. And we can answer this question too. The graph of 6x plus 1 is a line, right? This just goes back like a few lessons ago when we were graphing lines. This would, of course, be in slope-intercept form. A line is definitely a one-to-one function because you literally have only one member of the range having one member of the domain. Each member of the range has one and only one member of the domain. So this is definitely one-to-one. H of x is one-to-one, yes. All right, so that answers that. Now, we're going to do about, we're going to do about 6 exercises here, and then we're going to be done. So, these are all strictly going to be transformations. These will only be transformations, which means they're one-to-one mapping. So, we don't have to worry about anything that isn't one-to-one. So, we just saw how functions occur in one variable, like g of x or f of x, right? Well, guess what? Mappings, which are essentially functions, they can occur in two variables. So, you may see something like this. T of x comma y equals x plus 4, y minus 2. Alright, so you could almost think of this as t of x, but this is t of xy. This is a function of two variables, a multivariable function, so it does work in more than one variable. It gives you that the value for the function of x is x plus 4, the value for the function of y is y minus 2. With these mappings, of course, you have a change in both your x and y points. In a way, it's almost similar to vectors when we did that, when we talked about vectors in the last unit. It's kind of similar to that. But we're just putting this in a fancy function notation. So this is the transformation here. So we're going to graph some points. All right. We have the point A located at 0, 4. We have the point B located at 4, 6. And then we have the point C located at 2, 0. So here's point C. Let me label these points. B would be located at 4, 6. C is at 2, 0. Well, guess what you get? You're going to get yourself a triangle. That might help you illustrate if we just connect the dots. We're going to transform these shapes. So, this is your preimage, if you will, your A, B, and C coordinates at these given coordinates where A is at 0, 4, B is at 4, 6, and C is at 2, 0. This transformation function here of x and y, transformation t, you can call this, gives the change in the x and y coordinates for each coordinate. You will take this and apply this to each coordinate. So if we start with point A at 0, 4, that means we're going to put in 0 for the x value. If we put in 0 for x, that means you'll have 0 plus 4, which would give you 4. So you'll be at 4, 0 to start with. Then if you put in that y value of 4 into y minus 2, well, 4 minus 2 is 2. So you would end up being over at 4, 2 for your A prime coordinate. So A prime can be found at the point 4, 2. That A prime means the transformation has been applied. That is the image of A from 0, 4 to 4, 2. And this checks out because your x coordinate has shifted to the right 4 units. Your y coordinate has shifted down 2 units. So that checks out. Now, let's find B. If we want to find B prime, you'll put in the 4 for your x, which would put you at x equals 8. Then put in the 6 for y minus 2. Well, that would put you at 8, 4, which would be right here. So that's going to put you right here at B prime, would put you at 8, 4, when you put in each of these x and y values into the respective parts of the function for the x and y variables. Then we need to figure out C. So in order to get C prime, take this x value of 2. So put in 2 for x plus 4, you'd get 6. You'd be located at 6 on the x-axis. Then put in that 0 value of y for y minus 2, you'd end up being at 6 minus 2, which would be about right there. So here's your C prime at the point 6 minus 2. And yes, we can connect these and make ourselves a happy little triangle. So what this function means now is I have literally shifted this triangle, every vertex of it, 4 units to the right and 2 units down. So we also have to ask now, is this an isometry? Is this an isometry? Well, an isometry means it doesn't change the size of the shape at all. A way to do it is you can find the distance formula for each of these sides and find the length of each of these sides. Or a way to know it is look at the coefficient on your x and y terms, okay? If your coefficient is 1, whether positive or negative 1, if it's 1 and nothing else, if you're shifting, it's not it is an isometry because you haven't changed the size. If I put in another coefficient for these, it would not be an isometry. You would have a dilation, which we're going to get into. This is definitely an isometry because all we've done is taken these and shifted these 4 units to the right and 2 units down. You get the same identical shape. Now, we've done that. We need to find the preimage of 12, negative 6. So, find 12, 6. Find the preimage of 12, 6. Alright, so if we're going to be at the point 12, 6, right? For the preimage, because so far we've taken the image of each of these points and got the new shape, A prime, B prime, C prime. To find the preimage, you're going to set each of these values of x, the x plus 4 equal to 12, which would of course give you that x equals 8, and then you would set the 6 equal to your y minus 2, so y minus 2 would equal 6. So remember, to find the preimage, you set each function equal to the value that's given for the preimage, which would give you y equals 8. So the 0.88 would be, the preimage of 12, 6 would be 8, 8. When you set each of these x and y values equal to your preimage points. Alright, I got more here. I'm going to leave the first triangle up because we're actually going to use that for the entire exercise. We will use that for the entire exercises here that we're doing today. Alright. We're definitely going to have different values here. Alright, so let's see. We have a different function this time. We have transformation S of xy is equal to 2x plus 4 for the x part, and then we have 2y minus 2 for the y part. So we need to find the image of each of these points. So let's start with A. To find A prime, you're going to stick the 0 x coordinate in for the 2x plus 4. So if you stick 0 in for 2x plus 4, you would literally get 0 plus 4, which is 4. So x would be at 4 again. And then to get the y coordinate, you just put in 4 for the y. Well, 2 times 4 is 8, minus 2 is 6. So you would be at the coordinate, well, 4, 6. So interesting that B is also your A prime. So A prime is also at the point 4, 6. All right. Now, let's find B prime. So we got 4, 6. So take your x value of 4, put that in for the x. Well, 2 times 4 is 8, plus 4 is 12. 10. I need to expand this x-axis a little bit more, that means, because we're going to be at 12 for our x. So we'll be at x equals 12 for the x. Now put in the y value for 2y minus 2. Well, 2 times 6 is 12, minus 2 is 10. That's going to put me right there for B prime would be at the point 12, 10. So let's go ahead and start connecting these. Alright, and then we need to find C prime, which would be at 2, 0. Well, 2, 0, C, so let's stick in the 2 for the x. 2 times 2 is 4, plus 4 is 8. So that's going to put the x coordinate at 8. Now to find the y coordinate of C prime, put in 0 for y. 2 times 0 is 0, minus 2 is negative 2. So this would be at the point 8, negative 2. So C prime is located at 8, negative 2, after we've applied all these transformations. Okay, so now we have triangles ABC and A prime, B prime, C prime. Is this an isometry? I think looking at these, clearly they're not isometries. They're clearly not congruent. And in fact, remember what I told you, the quick test without having to apply the distance formula is look at the coefficients on your x and y variables. If they are both something other than 1 or negative 1, they are not isometries. They're not equal, because if the absolute value of the coefficient is greater than 1, you have a dilation. If the absolute value of the coefficient is less than 1, you have a shrink. So, definitely not. Now, we want to find the preimage of 12.6. So, we are going to find the preimage of 12.6. So 12.6 is the image, we need to find the preimage. So take each coordinate, the x coordinate of 12, set that 2x plus 4 equal to 12. Well, what's that going to give you? That's going to give you 2x equals 8, which means that x equals 4. And then take your y coordinate of 6, set that 2y minus 2 equal to 6, which would give you 2y equals 8, which means that y also equals 4. So the preimage of 12.6 would in fact be 4, 4. That would be the preimage, would be 4, 4. Alright, I got 4 more problems here. Actually, I think only 3. I think we're only going to do 3. Because I don't want to draw my x-axis that big. I want to have room to work on the board. If I did this next one, it's going to be another dilation, but it'd be even bigger and I'd probably run out of room on the board. So I don't think that's worth doing then, if I'm going to run out of room on the board. Whoops, I did not mean to do that. Dang nabbit. There we go. Alright, so let's see. The next function we are given then is h of xy equals negative x, negative y. So we have h of xy equals negative x, negative y. So we need to put in each of these values here. Dang it, I did erase the a, didn't I? I'm sorry, guys. A is at the point 4, 0. So let's find the image of each of these points. If I stick in the x coordinate of a, put in 4 for the negative x, I would get negative 4 for my x coordinate, right? I'm sorry. Wait. It's at 0, 4. I'm getting it backwards. Bear with me a second. That's 0, 4, not 4, 0. My bad. Okay, so if I put in the x coordinate of 0 for negative x, well, negative 0 is just 0. I haven't gone anywhere. But, however, if I put in that 4 for that y coordinate, I'll get negative 4. So my a prime is going to be at negative 4. So it'll be at 0, negative 4 for my a prime. Now, let's find point b prime. If I put in my x value of 4, so that would give me negative 4. And then if I put in my y value of 6, that would give me negative 6. So I will actually be at the point 4, negative 6, which is about right there. That would be my b prime, would be at negative 4, negative 6. Then, of course, I need to find my c prime. Well, put in the x value of 2. I would get negative 2 for my x. Put in the y value of 0, I'd still have 0. So I'd be at the point negative 2, 0 for my C prime. Would be at negative 2, 0. So let's go ahead and connect these dots. And there's my triangle A prime, B prime, C prime. Now let's talk about what happened here. The coefficient, if you take the absolute value of the coefficient and it's still 1 because you got negative 1 for your coefficient, you take the absolute value and it's still exactly 1, then they're isometries. You haven't changed the size. But these negatives denote reflections. So the negative on the x alone is actually a reflection in the y-axis, which we'll talk more about in the next lesson. And then the negative on the y is a reflection in the x-axis. I have simultaneously reflected this triangle in both axes. So it's a reflection, therefore, yes, it's an isometry. So now we want to find the image of 12.6. Find the preimage of 12.6. Preimage is one word, my bad. So find the preimage of 12.6, just set each of these, set the negative x equal to the x value of 12. That would of course give you that x equals negative 12. Set that 6 equal to negative y, so negative y equals 6. That means y equals negative 6. So the preimage of 12.6 in this case would be negative 12, negative 6. That would be your preimage. So pretty easy there. And you got a really cool reflection, which happens to be an isometry. Alright, I think we only have 2 more. We're almost there, folks. 2 more. Let's erase that. We're still going to keep the original triangle. They're in the red. Now we need to erase the one in blue, since that's the image. All right. We have here m of xy is equal to the following. You have 12 minus x for your x and just plain old y for your y. So we're going to find the image of each of these. So let's see here. Let's find the image of a, which would be a prime, 0, 4. So if I put in 0 for the x at 12 minus x, well, I would just end up getting x at the point 12 on the x-axis, which is all the way over here. And then I put in 4 for my y, well, that's just going to give me 12, 4. So my a prime is sitting all the way over here at 12, 4. Now, to find b prime, put in 4 for your x. 12 minus 4 is 8. Which would put me right here. Then put in 6 for your y. Well, that would put me at 8, 6. So let's see. You'll have b prime at the point 8, 6. Let's go ahead and connect those. Then let's find c prime. If I put in 12 minus 2 for where my x is, I would get c at 10, which would be right there. Put in 0 at my y, I would literally be at 10, 0. So here's my c prime, which is at the point 10, 0. So let's determine if this is an isometry. Well, look at your coefficients. The coefficient on the x is -1. The coefficient on the y is 1. So the absolute value of both coefficients is just 1. So yes, you have an isometry. That's a lot easier to do than doing the distance formula. Now, not only was this shifted, it was actually reflected. Since you have a negative on the x, you've reflected this in the y-axis. So it's been shifted and reflected in the y-axis, which we're going to talk in more detail about reflections in the next lesson. So this is an isometry. Now we need to find the preimage of 12,6. Alright, so again, take that 12 minus x for your function, set it equal to the preimage value of x of 12. Well, that's going to end up giving you x equals 0. Then just take your y, set it equal to 6. You literally get y equals 6. So the preimage of 12,6 would be located at 0, 6. That would be your preimage, would be at 0, 6. And I got one more example here. I know this has been kind of a long lesson, I'm sorry, but there is a lot to explain in this. Good news is there's only 4 more geometry lessons after today, then we're on to Algebra 2. So we'll be there very shortly. Some of you will miss geometry, some of you will be relieved to be back in algebra, but we'll see. Alright, last function here, we have g of xy for the transformation is equal to -1/2 x and -1/2 y. So that is our transformation function here of -1/2 x, -1/2 y. So let's go ahead and find a prime. So of course put in your 0 value for x into this transformation function. -1/2 of 0 is still 0. But what's -1/2 of 4 for your y value? Well, that'd be -2. So a prime would actually be located at -2. So 0, -2 is the location of a prime. Now, what about b prime? So put in your 4 for your x value in the -1/2 x. -1/2 times 4 is also -2, so that'll put you at x equals -2. Then put in 6 for your -1/2 times y. -1/2 of 6 is -3, so you'll be at the point -2, -3 for b prime is at the point -2, -3. Alright, so then what about c? To find c prime, take your x value of 2, right? So put in 2 for -1/2. Well, 2 times -1/2, that's -1. 0 times -1/2, that's 0. So this will put you at the point for c prime would be -1, 0. And then now we'll just draw a dot and connect these. And you have your new triangle here. A prime, B prime, C prime. You have the image. Okay, so here's the thing. Clearly these are not isometries, right? The new triangle, the image triangle, definitely shrunk from the original. We can clearly see it's not an isometry. And mathematically, look at your coefficients. Both of them are -1/2. So these are clearly not isometries. Now, these were also reflected again in the x and y axes. So it's kind of cool, all these transformations you can do. Now, we're going to, for the final time today, find the preimage of 12,6. So find the preimage of 12.6. Well, just take, again, each part of the preimage. So take your 12, set that equal to negative 1/2 x. Negative 1/2 x equals 12, which means that negative x equals 24. So x would equal negative 24. Now find your y value. So set that 6 equal to negative 1/2 y, which gives you negative y equals 12, which means that y equals negative 12. So your preimage of 12.6 in this case would be at negative 24, negative 12. That would be your preimage. So I know we covered a lot today talking about functions, mappings, one-to-one functions, transformations, isometries, and then explaining these different shifts. But the next several lessons should actually be easier. We're coming down to the last 4 lessons after today. The very next one will be about reflections. So stay tuned for that. I hope everyone has a great night. Take care.